to be able to code some deep learning model in Keras using TensorFlow as a backend. And to implement and transfer learning in Keras, which I added at the end because I think it's very practical for you to know that this is out there and not for you to try to reinvent the wheel. So I think we are more or less okay, but it's going to go this way. So each of them is one of the notebooks. So just as a curiosity, who already knows what deep learning is? Oh, okay. So yeah, thank you. No, and who has already programmed something with it? Okay, so yeah, you were just here around, I think, in the street and came in. Okay, good. But maybe I can give you some extra things that you can learn. And of course, you can always ask sort of an advanced question, and I will try to answer it. Okay, so for those of you that don't know deep learning, or I also see sometimes people that don't know deep learning but don't know sort of the history of it, where does it come from, who are the pioneers, and I think that's also a bit important to see who to follow, what blogs maybe to search and stuff. So that's the idea of deep learning comes from the artificial neural neuron, which came from really 1940s or 1950s already. And then there has been a revolution in the last, I will say, 2 decades with the introduction, especially, well, that will be 3 decades, in 1986 of backpropagation by Geoffrey Hinton. So I will say he's the father of deep learning. If you don't know, you should search him because he's everywhere. So I will say something like this will be more of, the one in black will be one of the most important. So I think especially this one in 1986, the introduction of backpropagation, and then now you can train these neural networks. There are other ways to train them, but this one really improved the performance. And that's one show, especially in 2012. That's where I think the breakthrough came in. So there's this competition, which is called ImageNet. So it's open to the public every year. And there's just to meet a model, and then you get some accuracy score. And when AlexNet was introduced, it blew away all the other type of models which were not based on deep learning. And that's where people started noticing. And then Microsoft, Google started grabbing the heads of these departments in universities like Jan LeCun, like Geoffrey Hinton itself, to lead their departments in AI. In 2014, this is of course very new, but this sort of a revolutionary idea, what is called generative adversarial networks. I won't talk about them. If you submit the question and I get enough votes in it, I will address it at the end. And then 2015, some clear sort of breakthroughs of, okay, you know, we're beating human actually capabilities. And I will say it became sort of mainstream and worldwide this 2016 AlphaGo. I think might be sort of just a news, kind of a clickbait thing. Of course, the algorithm is extremely complicated, but it really make a breakthrough for the layman to know, okay, now I have to pay attention to it. And especially Korea, for example, the revolutionized the country because they are very into the game of Go. And Jan LeCun, so he leads the AI research for Facebook and was one of the inventors of the convolutional neural networks. And he said, you know, this idea for generative adversarial networks introduced in 2014 is the best idea so far in the last decade. And it is really, really thinking outside the box because it allows us to do something that we were not able to do before, which is sort of penalize or have a sense of a loss function for something that we as humans cannot identify. Okay, so what is a deep neural network? So basically it's an artificial representation of the way our neurons work, right? So they have some connections to each other. They have certain current that flows from one to another, and then they can shut or not. So we have the concept of layers, input, output, so sort of a translation like that. So that's a feed-forward neural network. There are many types. We're going to see a bit more. And the neuron description basically is just translating that into this artificial neuron, where you have, well, anyway, where you have so some inputs that come from other neurons. Then you have here some nonlinearity that transforms these inputs into some outputs. And then this output basically connects to other ones, right? That's the basic idea. I think it's very easy to understand. It's nothing complicated. So the components of it, and I think everybody, I guess, knows these names by now, is the input layer, which is basically your features or whatever you decided that to be. It can be the pixels of an image. Can be also can be already features that you made with your data. Then you have the concept of hidden layers, which are the layers that sort of do the sort of calculation or they mimic the nonlinear function that represents the relationship between your inputs and the output that you want to get. And then you have basically the output layer, and that basically is, okay, I want to, let's say, do a classifier of a binary, I don't know, good or bad, or a sentiment classification, something like that. So that will be just one neuron, right? But then if you will have, for example, a classification now of different classes, let's say 10, okay, then there will be 10 neurons there. And it sounds very easy to say, but once you get to it, you need to understand what you want to get and how to relate that. For example, if I tell you, okay, which activation function do you use when you and your output layer for different categories, for 10 categories? Is it the same that you use when you do binary? No, it's not the same. So which one it is? Okay, and then so it has some relation. So we're going to see a bit about that. A bit more concrete, the artificial neuron, these are more or less the components. So you have certain weights. So that basically mimics the connections between different neurons. It can be strong connections or not so strong connections. Then once they get here, in this case, you sum them, and then you apply a nonlinearity. So this nonlinearity is called the activation function, which the most famous one nowadays is ReLU. So rectified linear unit. And you also have others like hyperbolic tangent as well, and other ones. Okay. So what is the idea about these layers? So the idea is that the layers learn hierarchical feature representations. So that means if I'm going to recognize a face, for example, so I start by recognizing shapes, like lines. And then I start recognizing maybe circles. And then maybe these circles together capture the eyes, or the ear, or the mouth. So you have certain schematic representation that sort of, they look more like your target that you want to identify in this case. So there are a bunch of neural networks, a bunch. Like if you Google, normally people will know just a few because those are the ones that sort of outperform everything else, but there are a lot of them. In these, today we're going to see fully connected and convolutional ones. But for example, in some other trainings, I also give a recurrent, long short-term memory, get a recurrent unit. I won't talk about them, but again, if you submit a question, then I can maybe say something 2 minutes or something like that. There are a lot. I don't know them all. I know them by name, but not like specifically. Some of them are actually quite old. Okay, so what is the typical flow for implementing these deep neural networks? So let's take this example. So in this example, we have 2 inputs. We have the first hidden layer made of 3 hidden units. Then we have connected to 2 hidden units, and then we have a single one. So this can be some sort of regression or can be also some sort of classification. Depends on the function that you put on your output layer. Okay. So what happens is that, so the input goes and gets multiplied by these weights, right? So at the beginning, these weights are randomized. And then they create this sort of the input for the first unit of the first hidden layer. Okay. So, and it's represented more or less by this function that you have here. And then you continue and you propagate forward. So you will do this for every neuron in the network. And you propagate forward until you reach the end. Once you reach the end and you have your loss function, you will be able to say, okay, this is the error that I have. right? This can be the classification. If you have, for example, generative adversarial networks, that works completely different. But if you have sort of a regression that you want to apply, that can also be done. But then that will be maybe R squared or something like this. So yeah, you have your error. And now comes the backpropagation, which is the 1986. So that delta, that error, now you want to calculate that error for each of the neurons in your network. Why do you want to do that? Because then you can calculate the gradient of that error, which will point you then to the correct direction that your weight should move. That's basically it. So in this case, for example, this will be the error propagated to the neuron 4. Oh, sorry. And the same thing. But of course, because there are more connections every time, then it gets a bit more involved, right? And you can imagine if this gets really wide, for example, and deep, this basically gets really, really sort of complicated in the sense of how the dependencies are throughout the network. And then you go all the way back, and then you calculate the derivative, or the gradient in this case, for that specific weight. And then basically you apply what we all know from linear regression, for example, this basically the optimization rule. You have your derivative over your last function that you propagated all the way back, so for that specific neuron, and you basically then add certain coefficient, that will be the learning rate. We all know that from linear regression. And then you basically adapt your weight. And that's it. And then you do it for each one. Okay. So now if you see here, there is a lot of dependencies, right? Because the penalization of the weight for, let's say, that connect to neuron 1 will depend on other weights, for example, from neuron 4 or from neuron 5. Yeah? So far, so good. So how do we actually calculate this? So actually we calculate this by using what is called the chain rule, which is sort of a basic way to calculate derivatives that are dependent on other functions. And there are different ways to do this. One of the ways is to do this numerical approximation, that if everybody took a bit of calculus, I guess that was the first equation, and you were like, what is this h, and why does it limit to 0? But anyway, so that's one way, which is really expensive. And is also prone to error, because what I just said, so normally you will see a limit there, I forgot it, so sorry for that, for those mathematicians here. So limit of h going to 0, but then it's a computer, right? So what does it mean? What does it mean that's h leading to 0? What's the actual value I'm going to put there? It turns difficult. And I've done it myself during my PhD, and yeah, you don't want to do that. Okay, so instead of that, you have what is called symbolic differentiation. Symbolic differentiation means that you have the actual function that is the derivative. So for example, if my function is, I don't know, x, for example, I don't go and do x plus h, x minus h divided by h. Instead I say, well, it's 1. So you declare it somewhere else that the derivative of that function is 1. Yeah, so it's symbolic. So what that allows us to do is that we don't need to do this numerical approximation, and it's much faster. So that's why, for example, TensorFlow does. So if you go into the TensorFlow source code, every layer that you're going to find there, activation function, the derivative is defined. You are going to find it because it uses this. Because if not, it will take forever. And it's also prone to error for what I just said. So there are some, what I will say, but maybe somebody that is more expert than me will say, no, it's because of this or that. I think there are some sort of conventions. So for example, when you have the ReLU, the derivative, if you know the ReLU looks like this. It goes like this until 0, and then it goes like that. Okay? So what's the problem with the derivative of that? Exactly. So, right? So, okay, now how do you do it? Right? So if you go to the TensorFlow code, there's an if. Of course, right? To my physics and mathematical background, it's like, ugh. But it is, and it's a convention. You can see it there. Okay, so you can find it, and that's why it's a bit much faster than if you do numerical computation. And
so the difference
The issue is that if you evaluate the derivative on 0, you have to make a choice. So they make a choice.
And it's not an issue, apparently.
Apparently not. Apparently not. Probably, like I said, probably someone that actually implemented this will let you know more. You can ask them in GitHub, of course. Maybe there's already one there. But no, apparently it's not an issue, and it's not the only one. It's not the only function that does that. Okay, so how this backpropagation, so everybody good with the backpropagation more or less? You get it back, you propagate your errors, they calculate the derivative, and then you move. Okay, so how this backpropagation actually works? So first of all, like I said, well, you need to define these errors, right? So then for that, you can define you have to define your loss function. So then you can differentiate the loss function, because if not, how do you know what the error is? If you haven't defined, basically, okay, you know, is R squared, or is binary cross, categorical cross entropy, or binary, whatever you want. So that's the first thing, and there are a bunch already in Keras. Then for that, and then the next thing is you're gonna have to define your optimizer. How am I going to run the gradient descent, right? From linear regression, we know stochastic gradient descent, or gradient descent by itself, right? Gradient descent, if we know, yeah, it's taking basically all the data, and you do one optimization step for all the data. A stochastic gradient descent says, okay, we're going to use batches, right? And then for each of the batch, I do a step, and I move, right? That's why it's a bit more zigzagging if you see the loss curve. But there are other ones. So we have several, like stochastic gradient descent with momentum, AdaGrad, RMS prop that works well, especially for recurrent neural networks. Adam, which I will say is more or less the de facto right now to use. I think it's also the default in Keras. So all of these, I won't go specifically because we have little time, but all of this is just the stochastic gradient descent is the same rule, but it adds a bit of momentum to the search. So when you do a stochastic gradient descent or gradient descent, what you actually are doing, you have a surface and you're trying to find the minimum of that surface. And what it's doing is moving and it's checking. Is this lower than that? And then it moves. Is this lower than the other one? And then it moves to that point and stuff like that, right? It continues. Okay. So, but what this actually potentially can do to you is that you get stuck, right? Around a valley. So when you add a momentum to it, it's more like searching with a bicycle. So you have a downhill, you're going with your bicycle, and you find sort of the valley, and you continue a bit more, and no, it still goes up. Okay, then I go back. But maybe it has the momentum enough to cross this local minima. And then it finds maybe the other one. Yeah? All of these are on this principle. Just the way they implement momentum, that's the thing that is different. Goed zo? Okay. So, yeah, the only word I know. Okay, so this is some example of that. So, for example, you can see, especially as thing in the picture on your right, you can see the difference, right? And that those surfaces are special surfaces that are made to test this sort of minimization of functions. Even before I knew deep learning, I knew the other one, which is, we call it in Mexico the horse saddle, because it has this. Yeah. Of course, that's not how we call it in Spanish, but yeah, that's basically the translation. La silla de caballo, I think is. Okay, so you see the difference, right? So you can get stuck. And especially for surfaces that are very complicated, that's a big issue, because you're going to have a lot of bumps. So a surface where you have, I don't know, 20 layers, and then each of the layer has 30 units. So that means, I don't know, you're going to have, and then you have some maybe convolutions. Maybe you end up with 3,000 weights. So that means 3,000 dimensions on this surface. It's very prone to have local minima. Yeah, so it's very important. So in my opinion, never use a stochastic gradient descent. I think I will submit a ticket in Keras that they should remove it or something. No. Okay. So, okay, so that's Braille's how you train them. So I think this is a very important slide, especially for people coming, because you see and they get impressed, and you go to these talks and these guys using deep learning. Why am I not using it as well? And it's not for everything, at least in my experience. Okay, so the data types, we can separate them in structured data and structured data. For structured data, you will normally use handcraft feature engineering, right? So, and normally the best algorithms that perform are boosting algorithms, okay, or ensembles methods, okay. If you don't know what that is, you can search it. I'll also add the link here where you can have a read. It's a bit more complete. And when should you use deep learning? When you have unstructured data. Yeah. So when you cannot come up with what are the features of this, maybe it's a signal from a heartbeat or something like that, or maybe like an image, of course, that's the obvious case. Text as well, right? How do you define the parts of a text? How do you find the actual meaning of a certain word when it's sarcastic or not? Right? That's incredibly difficult. So this is for these cases. Okay. So I will say in a general way, especially if you're just starting, images, text, and signals. And you can see this link, which is quite a nice explanation. And about the data, so a good performance can be achieved normally, like in a general rule of thumb, with 5,000 labeled data for, in this case, supervised learning. For unsupervised, we don't even talk about that, because now you're talking about reinforcement learning, and those actually have to happen in a fake environment that you can repeat as many times as possible. And now you're talking about billions of experiments. So I'm talking supervised learning here. Okay, and for really to get into human performance, we're talking now about millions. Okay, now I will say this is true if you start from scratch. This is not true if you use transfer learning. Okay, we're going to go a bit what that is. The recommended literature that I'll definitely go have a read. I don't think it's that heavy in math, but it does have some linear algebra in it. But yeah, that's the book I would recommend you to buy. And some trainings, of course, my trainings. Anyway, so there's one in the Dutch Data Science Week. And I think, yeah, so next, May 29th, so pretty soon. And the other one, so you can just take a look. Okay, so we're going to talk now about deep learning tools. Questions? Not so far? Good. I don't know how we're doing in time, but let's see. Yeah, I forgot about that. Should put it here. Okay, this is a short one. So, deep learning tools. So, deep learning tools. There are several. There are many. There are more than this. You have also Café, MXNet, etc. But if you are going to start, choose one of these: Keras or PyTorch. Well, TensorFlow as well, but you can use Keras with TensorFlow at the backend. TensorFlow is sort of what is the phrase? Nails and bolts, something like that. Of if you actually want to build that from something from scratch. So for example, the other day I was researching some not researching, but I tried to build something to translate a researcher idea into a neural network, and of course it's not implemented. So I had to use TensorFlow, for example. Right? But for any other sort of standard use cases, I will say go to Keras or PyTorch. Okay. For today, we're going to touch on Keras. So why are we going to touch on Keras? Basically, one of these explanations. Basically, because it's very popular, and it's, of course, that's like, okay, you're all going in the popularity trends, right? Now, but that means also there is a big community behind it. So there are issues you can search. There are going to be less bugs, of course, because it's open source. So every open source, of course, and also non-open source has bugs. But so there's a large community, and especially recently has has taken a nice boom with the TensorFlow background in the backend. So basically that's what we're going to do. We're going to use Keras with a TensorFlow backend. You could also use Torch, for example. So we're using also like the top two, right? So also this is basically the community contributors, forks, issues, and activity, right? And if you start using it, don't be afraid of submitting issues, huh? Like if you check issues, some issues are like really a question maybe that the guy that made it didn't thought about it. And you can help the community by doing that. So visualization about this, what I like is that TensorFlow just comes with it, right? So it has a tensor board where you can just see how your models are training. You actually can see it real time, how the models are training, the loss curve, how is it performing. So you could stop it, for example, if this takes, I don't know, a couple of days or something like that. You can also compare with other runs that you have made. And also has, I don't know if you guys know what word embeddings is, but it also has visualizations for this. So it's very complete. From PyTorch side, you have Wisdom, which I haven't used, but it's far more customizable. But of course, comes with a penalty that, well, you have to do it. Okay. So in general, one of the things that I will say is that why do I sort of, I think PyTorch is gaining a lot of popularity. Yesterday I was in a deep learning meetup here in Amsterdam, and they were using PyTorch, for example. There was in the university, so research. But for me, it's like TensorFlow. I mean, the people that is behind TensorFlow. I mean, it's Google. I mean, you know, they're releasing these things like crazy since they took over, right? Now, I mean, it's what, 1.4, I think, I don't know, a year and a half ago. Now I think they're already 1.7 or something like this. They're releasing like crazy. And it's getting better and better and better. And you're going to see, for example, especially for the transfer learning case, how easy it is to have this TensorFlow in the backend. It will just work. Of course, there's also some issues like everything. Huh? Okay. So this is going to be the first exercise. I think this is what you were waiting for. So of course, if you already had Keras and TensorFlow installed, you are going to be able to run this. If you didn't, then it means that there's an environment file there on the repo, and using Anaconda, you basically will have to run the command, conda env create -f environment.yaml. So that's a bit maybe a mouthful, but basically, so let's say, for example, no, not projects. You cannot see that. Repo, oh. Okay. Yeah, so there's the environment file. You can see it there, right? Now you will do something like conda create -f that. So if you don't have experience with Anaconda, maybe ask your buddy in the site. I can also help you as well. And so I'm gonna leave you guys to work on it. Let me see what I wrote in the schedule. Hopefully we're in time. And for others, please raise your hand. People that don't have laptops and questions. It can be about anything. What is the actual impact? Where have you seen it used? Where have you not seen it used? What are you going to talk on San Francisco? What is these other LSTMs, recurrent networks? So I can talk while other people is working on it. So let's check the issues first. Yeah, and I see some faces that I know you know how to create a virtual environment. So help the others. I know you. Let me write it down. But let's see. Let's see if there are some issues already. Oh, nothing? Okay, so no questions. Good. Oh, first, run the cell first so you can see actually like nice images. Because if not, you're going to get it in your face. So basically this notebook is very basic. So if you already, like if you take it like really quick, just go to the next notebook. You have the link at the bottom of the notebook. But this basically will try to teach you how to build a model. How do you add these so-called layers? Right? So try to run it. If you cannot install and you're sick of it because it just doesn't work, and because you have a Windows computer or something like this, which is normally the reason. So you have some links here where you can read. Maybe you read something about it and then you ask me a question. And you have all other links about the layers. Yes.
In a nutshell, what is the difference between Keras and PyTorch?
So for Keras, are you going to see in that notebook? Once you create a model, you need to compile the model. So you cannot sort of change it on the fly. PyTorch allows you to do this. Yeah. So PyTorch, so in a sense, you can layer, train, then add another layer, train, without this compilation. It's not following.
Exactly, it's a layer. I mean, I understand the neurons, I understand
Yeah.
the connections. What is a layer?
So the layer is a collection of neurons, which are, so if you have, so this will be a layer, this.
What makes them different? I mean, I see dozens of different layers.
Yeah, yeah. So you can have, for example, this is called, somebody knows what these layers are called? You answer yourself. So yeah, fully connected layers, yeah. So then you can have, for example, a dropout layer, which is, well, then I will need to explain what dropout is. But basically you put sort of I will say a gate, which randomly throws away some of the lines. So for example, that's because you want to, it's for the reason of overfitting. So you don't want, so for example, this one is learning something very, very specific, and it comes from certain part of the image. Now let's say the image changed a bit, and this doesn't fire anymore. So it's really, it's overfitting on that particular image. So you want to sort of throw a weight sometimes, such that other neurons learn to compensate. So that's an example of that's a dropout layer. Okay, then you have, for example, all activations are also layers. You can see them, they're also there. Then you have, for example, an LSTM layer. So I won't explain what LSTM, but you can basically have your LSTM layer, and there's a whole machinery going on, and you say, well, after my LSTM layer, I want to connect the outputs to a fully connected one, for example. I don't know, you can say one more that is there. Convolutional, for example, right? You have a conv? Yeah. So for example, you have your image. We're going to use that, right? And now it comes into a convolutional layer. So you just throw it in. Like, okay, this will do just the convolution. And this sort of, and then you say, okay, I want another convolution. And then maybe you want a fully connected. Yeah? So it sort of hides this machinery of each of the...
So it remains in essence the same, but it's sort of...
not the same in the sense that how this works, right? But in the sense that they're stacked.
Okay.
Yeah? But if I would, for example, if I say, okay, what is in here? Yeah. Yeah. So these are recurrent, for example. This is actually an extended where they connect to themselves in previous step. So that's what I like a bit about Keras. So you know the theory, you know how they work, and implementing it is, yeah. But this is also sort of, I will say, a bit of a problem, right? No, because people just throw layers in it and doesn't really know why, right? So I think I'm not sure, but maybe there's an example here. Yeah, I think I have an example where it is going to be something weird. The validation is going to have a higher score than the training set. Yeah, so let's say you throw these layers, right? Because you read it somewhere, and you find this. And then you're like, okay, and then you show it to me, and I ask you, why? Why is this? Yeah. So it's because of how one of the behavior of the layers. But, so I will say that I like Keras because it makes the implementation easy, right? You don't, as a data scientist, I think I think by now I hate computers, right? Yeah, because the problem is our computers. The problems are not the theory. But anyway, so Keras makes it very easy for you. So if you know the theory behind it a bit, it's just throwing it around. So for example, one of the things I think I ask during the notebook, you can see the summary of the model. Let me show you that. For example, let's just start with this. I mean, even the simplest. I try to add a layer, and it doesn't work. Why? Why it doesn't work? And you have to think about the concept. Well, because just the concept of it, it doesn't know what inputs it's going to get. So just the concept of it, this doesn't make sense. So you can define your own input layer, but then below I do it, Keras does it for you. You just add, oh, I expect this. I expect this amount of dimensions, and Keras will do it for you. But you do need to know it, because let's say you hit this error, right? The first layer in a sequential model must get an input shape or batch input shape arguments. Yeah, sure. So you add it, and why? What value should it be, right? So it's because it's the amount of inputs that you're going to get. In this case, we saw these are 2. Yeah? So these are the inputs. So if you see the first hidden layer here, you have input 2, but the amount of units is 3. So I'm creating this sort of interface. Yeah? So it makes it easy for you. You could also define 1 by 1, but for the input it's not necessarily. You can also, for example, this question below. That's when I catch sometimes, that's sort of my first question sometimes, also for some interview or something, when they say, oh, I know deep learning. Ah, good. So, okay, so then I ask them, just this simple, why are there 9 parameters? Okay, so, yeah, and how does come up to 9? So yeah, no, you're in the correct path, huh? So you have these 2 connections, right? It's already here. Why do I like to draw, I guess. So you have these 2, right, and 3. So how many weights are there? 6. So why are there 9? Yeah, somebody said it. The biases. And then you're like, ah. Yeah. So actually, each of these is more or less like a logistic unit. Right? It's weights times the features plus a bias. So that's where they come from. Okay. Now, when you would implement a convolutional, there are also parameters and also the question. I think you get to understand when you throw a layer and then you see the parameters and you're able to try to understand, okay, why are these among the parameters? Because you do need to know what's happening in order to do that. You could just don't care as well, but I would think you would like to care, but that depends. Yeah. So about these sort of layers, yeah, they're all there. Yes, they are all there, and they're there for you to access. And for example, one of the difficulties that I see sometimes when people try to implement convolutional layers is the input-output, the dimensions, because you need to define the dimensions. He will tell you, I expect this, but I receive this. And that's a bit, I will think a bit more tricky for people that are just starting up. And that's because how does the actual convolution works, right? So you can try it. I think it's one of the exercises. later, I think. But you're probably going to hit this problem. I even hit it now, and it's, oh yes, I forgot this other dimension. But so data, the parameters. So optimizers, the same thing. They're there for you. They have your back. More questions? No? Okay. So what we're seeing right now, like I mentioned here on the top, this is the sequential API. Keras has two types of APIs that I know of. Let's say it like that. Sequential and functional API. The sequential API is the easiest. The sequential API is the one that, it's sequential. The one that is one after the other. Okay? There's no sort of coming back or branching and then reconnecting. Yeah? So, so for most of the, for most of the use cases, sequential API is enough, given that you know what the layers are actually doing, like you said. So for example, but if you want to build, for example, let's say you want to build this. Can you build it with a sequential API? Of course not. It's not possible. Right? So you need to do the functional in this case. Is this actually a model we used for what a colleague used and built for detecting anomalies in the heart from MRI scans for a project. So you cannot, right? You have to use the sequential. You have to use the functional, right? But we're going to stick with the sequential for today. Yeah.
How do you come up with a schematic like that? Is that domain knowledge? Or?
Yeah, so that's research, and that's domain knowledge and just trying. And there are already some sort of older architectures where they do something similar. So they sort of build on each other, right? So for example, if I show you, let me see. Actually, it's a good time to see. Ooh, should be in the next one. Okay. But anyway, so if I show you this, for example. Oh, I don't have it. Okay. Maybe it was loading. Wait. Yeah, I was loading. Okay, if I show you this one, for example, right? That's Inception V3. It was made by Google 2015, I think. At least the paper was 2015. Okay, so if you see, they build on top of each other. So these, for example, this architecture that you see more or less that repeats was already before. Somebody introduced it, and this has to do with convolutional and the pooling from layers. And then you say, okay, why don't we stack them together, right? And then you see this tail here that looks like that. This is also a question I ask sometimes. What is this? Because everybody talks about this. What is this? Because it is there. It is there. Why? There's actually, this is not complete. Sometimes it goes, there are more in the back. And it's strange, right? Why? Why would I have two outputs? Because actually this is a softmax. So softmax is once you want to make the classification, and it's in both places. So why? Why would they want two outputs? Once we go to the transfer learning, I'll answer the question. Okay. Let's see. I'll help you out a bit. So the different activation functions, like I said, there's softmax, there's relu. That somebody knows now, that because I saw that someone had experience, why is for example, the hyperbolic tangent not preferred over the relu? Or what is the problem with the hyperbolic tangent? No? Ah, nice. Yeah, it is because of that. So, the hyperbolic tangent has this sort of look. right? So it's flat here, and it's flat here. So what's the problem with that? Yeah, this guy. You should talk to our chief scientist. Huh? We're hiring. So this is, yeah, because the derivative is 0. So it means that when you remember, you propagate back and you calculate the derivatives. And let's say for some reason your input goes into these parts. What is the value that is going to multiply by? 0. So what is going to be the propagation back? 0. Is it going to learn anything? No. And then your model is stuck. That's called the vanishing gradient problem. Okay? It has two sources. One is this. One is this. There are other sources. And the other source is actually solved by what I just showed you about having the extra branch. But anyway, so this one here. Yeah, that's okay. But the problem is that if they go sort of say in this sense, you don't want them. But the thing is, here they're on both sides. And that's sort of the problem, because yeah, that's the other issue. So when you have a matrix, right, and you're multiplying values, let's say these values are lower than 1, right? So they're gonna go to 0 basically, right? But if they're very big, or they're bigger than 1, when they multiply, they're going to end up in this area. Right? Yeah? So they're going to end up in here, which this does not have the problem. Yeah? That's the other, when I said the two sources, one is the source is the activation function, and the other source is the multiplication, because since it's so recursive, there's going to be a lot of sort of multiplication of weights to get to that one. So if the weights are lower than 1, they're going to tend to 0, and they're going to vanish the same way that this makes it vanish. So that's the other source. Or they can be bigger than 1, and then they're going to explode. So there you have two problems: the vanishing gradient problem and the exploding gradient problem. And so that's why.
But isn't there a case where you'll end up in the left?
Yeah, but then yes. So that's when you have what is called leaky ReLU. You can say, did you look at your activation functions? No, leaky ReLU. So it defines sort of an angle in here. Yeah. There are many ways to deal with that, but the ReLU, for example, takes away those 0 tails. But good questions. Okay. So this is when I said about the compiler. I remember who asked about the difference between PyTorch and, right? So it compiles. So I say, use the optimizer atom. Here's when you need to know sort of, okay, what are the activation functions? How do they work? Why is it binary cross-entropy, right? Depends on what you're going to calculate. So for the next example, for example, we're going to use, I think, cross-entropy, which is for more than one class. And if you really want to get into the details, then you do the config, which is helpful as well. And notice this one. Notice this parameter here. Trainable. So it has a knob to turn that weight, to freeze the weight. So say, I like this value of my weights right now, so I want to freeze them. I don't want to optimize these weights. So that's basically what we're going to do in the transfer learning. Okay. So in here, I created this data set, which is not linearly separable. Okay. So basically, I create the typical test set. Now, also, by default, Keras comes with what is called callbacks, if someone of you is already familiar with what a callback is. But basically is that at a certain point in time during the training, it's going to call a function, and then it's going to do something with that. So Keras already has, for example, for doing the tensor board, already has it for it, because you need to save it into some logs, how your training is going. So Keras already has that. So you send it as a callback, and it's going to sort of save the accuracy that it's having during training time in that log. And then TensorBoard is just going to pick it up in real time, and it's going to update the figure. That's how it works. But you can say any type of callback. So this I created my own callback. You can see it in the utils module in here. So how it looks. It should be somewhere there. So it's this one. So now it's yours. You can use it. No problemo. And you add it as a callback. Okay? Now, if you see, once you compile, you use the model fit, right? Very easy. And then you just send the training data, the number of epochs. So the number of epochs is the number of times you're going to go through the whole data set. So for example, let's say you're not shuffling your data set when you choose a batch. Let's just say you separate it in 5 batches. So you say, okay, I'm going to say I have, I don't know, 1,000 observations, and I make batches of 200. Okay? So then I have 5 batches, and each 5 batch, that's an epoch. Yep. Because you're going to see this when you read stuff. Right? So an epoch is not each optimization time. It's optimization step. Huh? It's once you go through the whole data set. So in this case, I have a batch size of 100. I don't remember how many observations I had. And I'm running 10 epochs. Okay, if you see also out of just very simply, you have validation split. So on training time, it's going to separate in a validation. So it's going to sort of optimize for certain part of your data set. And for the other one, it's just going to calculate whatever score you want to calculate. In this case, is accuracy. So that's why if I put variables 1 in here, for example, right, you can see this validation stuff. So if I wouldn't add that, right, I don't have it. It uses the whole data set to train. Yeah, that's why. Right, so there you see it. Yeah, in this case, doesn't do anything, but I don't know why. But anyway, so okay, so then you have the curves. Let me just close this. Okay, it's not improving. But this is better. Okay, so you're going to have these curves, which are the basically the learning curves. So in this case, I'm just going to write. Okay. So in this case, if you see now, I defined. Normally, you will define the model like this, like just in one go. So before I did it in certain different cells, just to sort of take you through it. But normally, you will do it like this. Let me see. Sure. Okay, so also these curves that are here are made by this function I made. So this is also yours, you can use it. And then you have what is called the learning curves. So this, in this case, is the accuracy. So how many times I'm guessing the class correctly, right? And then you see the curve for validation set and training set during training time, okay? So, and then the loss, right? So in this case, we set, I think, binary entropy, cross entropy. And we have the loss function here. How is it behaving? So when I see this, right? So it's not flattening out. So it appears that still it's going to go down. So you probably need more epochs in this case. Right? You also might see something, maybe we can see it here. But then I'm going to show you the answer. Okay, it's fine. Okay, so now what I did is, not really what I expected. But so sometimes you might see a really zigzag function, curve. So something that it is going down, for example. I don't know if it's going to happen with this because the data set is sort of pretty prepared. But yeah, also because of the amount of classes, there are not many. You might see something, for example, let's say the accuracy, that looks maybe like this. Yeah, you might see something like that. So, any idea what this might be, the problem? This is, let's say this is accuracy. So this normally is because, remember, the weights get updated on every batch. So it means that each of these points is what happened for every batch. So it means your batches are too small. Right? So it is moving in the correct way, but because your batches are too small, they're not capturing the actual representation of your data. So in average, it's moving to the correct position, but it is sort of taking these steps where you're not really optimizing for the data itself, but just this batch that is too small. Yeah? So you might see this. I've seen this several times. So this means just increase your batch. Okay, so I think we are so. Okay, so now we have this exercise 2. So maybe some of you went over it a bit already. So I want you, so these are 2 classes, of course. You can separate them some other way, but I just wanted you to learn how to add other type of layers. So what I wanted here is just make an overkill model, so a model that is just extremely big for these 2 classes and something like that. So the idea is that we're going to create 3 hidden layers. We're going to use batch normalization. We're going to add the dropout layers. And we're going to use ReLU and also the hyperbolic tangent. I don't care about the accuracy about this. It's just for you to actually make it run. Okay. So what batch normalization is? Batch normalization layer, so yet another layer, is basically you have your sort of your input layer, or I don't know, something, and then you have your another hidden, whatever, something like that, right? And let's put it here, for example. And let's say you have these connections, something like this, right? And then these the activation of these neurons, right, is going to be multiplied by these weights, and then they're going to enter each of the neurons, and then they're going to be squashed or by this nonlinear function. This can be ReLU, which can be the hyperbolic tangent. Okay? So, for example, when you use the hyperbolic tangent, like my friend here explained, yeah, these sort of are a bit of a problem. There's another problem with, but I'll mention in a bit. So you will like the inputs to this to be around this area. So what the batch normalization does, it does what you do when you, in a linear regression, when you scale your features, exactly the same thing. It does exactly the same thing. But it does it in the middle of the layers. So if you add a batch normalization layer in here, it basically rescales this such that, well, depends on the type, but let's say such that it has mean 0 and variance 1. And then it throws them into here, such that you do have the data around that point.
Does it rescale all together, or just neurons are independent?
Independent. So it's exactly the same. It's per feature. So now the feature is each of these, right?
Yeah.
So it's exactly the same. So it's like, forget about that you had that, and now you have sort of, let's say this is the input, and you're scaling your features. Yeah? So this achieves this, right? Because you don't want it to be extreme. But what other things, why do you scale in linear regression? Well, I said I was not going to explain basic stuff of machine learning, but why do you scale it? Why do you scale your features? Again, it doesn't matter, huh? Normally I will help you out. No? Okay. Why? I see you. No? Okay. So normally you scale it because 2 reasons. If you're using regularization, right? So the regularization penalty, the coefficient, is the same for all features, right? Or not? All right. It's just a term, which is like this. It's alpha. Is that? right? It's weight index independent. So if you don't scale them, this value can be very big for some features or can be very small for some others, which means the penalization term will be huge for things that are scaled big, and for skills that are actually small, then this will be quite small, right? So the penalization term. So there's another reason, and the reason is also the loss function, and that's what that is related to the neural networks. So if you have, let's say you don't do regularization, you still want to scale them, because when you're doing gradient descent, we have what is called the learning rate, right? We already know. Right? So you have, and we also introduced it in the equations. So you have your weight I equal to weight, plus 1, weight I, right? Plus some learning rates, in this case I will call it alpha as well, times the gradient of your loss function on the weights. Right? Okay, so is this learning rate independent? Yes, right? It is the same for every feature. So it can be, if this turns out to be proportional to the value of the weight, or of the value of the feature, for example, then it means that I'm taking really big steps in one of the dimensions of the features and really small steps for others. So I might be looking in really, what is it, anisotropy? Or not in a symmetrical way, right? And that's when you see these figures that when you normalize, then you have this loss function that looks like concentrated circles. I mean, everybody has seen that picture, probably. So it's the same thing for neural networks. You want to do that as well, because also your learning rate gets applied in the same way, right? There's also a derivative there. Okay. We're doing a bit short on time. Okay, I'm just sort of going to paste it and explain really quickly. Please keep the questions coming. If I need to skip something in, that's fine. I'll also be around, so you can also ask me something. So, right. So this will be more sort of the way to add these layers, right? So we have here, we define first sequential, right? We start with that, start fresh. Then we add a batch normalization. You can give it a name. You can also put it without the name. Then we what is the input shape? So like we said before, the input shape is 2, right? And then the first layer has 30 units, the second layer has 10 units, and the third layer has 3 units, right? And within each of those layers, I add a batch normalization, what I said before. Then I define the activation function. If you see, the activation function is no longer inside the dense layer as before. You remember? You see how I gave it in the dense? Why is it not there anymore? Yeah, because the batch normalization, right, needs to happen before the activation function, right? Because of what I just explained. Okay. And then the dropout, which basically is what I explained about dropping some of the connections in order to not overfit. And then you can just run the same. I don't know what was the accuracy of the other. No, more or less. But the batches are smaller of the other, right? Yeah, so this is the batch size of 100. Let's make a full comparison. Yes?
So if you leave off the activation equals argument to the layer, then it's linear?
Yeah,
There's
exactly.
Okay.
There's none yet. Exactly. Very good. Yeah. You can build also a network without activation function. They will just explode, but yeah. That was the starting. Like if you go to the initial papers, that's where it starts.
No linearity.
Just connections. Like okay. Yeah, but you're talking decades, huh? Yeah. Okay, sorry. So if you see, for example, we added this super overkill, and then I think now I have the same, 100 batch size of 100, epochs of 10 epochs. I think even we could do it with 6 or something, maybe even 5. Let's see how much it takes. And then this should already outperform the other one. Yeah, it's already 0.8, right? And this one is big like that. So, okay, so I have to move to the other one because we're a bit behind schedule. Actually, lots. So I will try to run a bit fast through it. Okay. Okay, so we learned what we've learned in the previous notebook. So we learned basically how to add layers to a model, right? Where do I find these layers? Where is the documentation? Where I can read about it? How can you, let's say, tune it yourself? You can add the activation function within the layer. You can add it yourself if you want to introduce batch normalization. We saw what batch normalization does. We saw what dropout does in a high level, but we did see that. So it's now just about you reading a bit about more about these layers and, okay, this might be useful, this not, because you also have, you say convolution, for example, but then you go to search for it and then you will find one-dimensional convolution. It's there. I think you saw it in the layers. Two-dimensional convolution, three-dimensional. So what does it mean? What is the difference between them? So that you have to read about a bit about that. Okay. So this is basically, in this case, digit task. In this case, I also have this one, which is actually a pretty hard data set, this one. This is the CFAR10 data set. It's there for you, just out of the blue. You can just build on top of it. It's pretty difficult. It's not an easy data set. But just for sake of showing right now, everything should run if you just uncomment this one. So it's just there for you. Okay, so first what do we need to do? So we're going to prepare the convolutional layer, right? So normally you will say, okay, I'm having these inputs, so I need to have like a one-dimensional structure in order to have my inputs. In the case of convolutional networks, you don't, right? Because that's actually what you want. You want to take advantage of these channels. So in this case, what I actually do in here, if you see, I reshape the data such that, yeah, this is the amount of data. This is a 28 by 28 image. It has a single channel. If you see the data at the beginning had no channel. Yeah, because it's just a single, so by default it reads it like that. But if you want to use this sort of 2D convolution that we're going to use later, you have to add this channel. If not, it's just not going to work. It's going to tell you I expected this extra dimension, and it's not there. Okay, so we also need float numbers. And if you see what I did is I also rescaled the pixels to be from 0 to 1. So far so good. Okay, so now the idea is, and I will add it. I can do it maybe here. So in this case, what I'm doing is adding sequential, starting with the sequential, then I add a batch normalization, the same dropout. Now, if you see the difference, now we have this convolutional layer. And it's easy as that. You just add it to it. Now, the difficulty a bit is to see about these, the kernel size, the number of filters that you have. So the number of filters, I won't explain convolution because it will take us the whole session. But it's basically you go from 3 channels to 32 channels. That's what the filters are. So there are 32 different kernels that are going to be applied in your convolution. If you didn't understand what kernels are, it's basically just a smaller neural network that is going to go through your image. Yeah. So you're gonna have these sort of not very deep, right? You have 28 by 28 by one channel, and then I'm gonna convert that in this case to a deepness of 32. And what the kernel size is basically I'm gonna form sort of a square of 3 by 3, and then that is going how am I gonna move across my image. That's the convolutional part. And what you use an activation, also of ReLU, and border, that's how, when you hit the borders of the image, so for example, if the size of your kernel is not a multiple of the size of your image, it needs to make a decision. Do I stop? Do I pad it? That's basically what this does. So there are different options. So this one, for example, just stops when it hits the border. Did I already create this? Okay. And then you have what is called max pooling. So what the convolution does, it multiplies this kernel for the image, right? So let's say I have a 3 by 3 and it multiplies. So I'm still gonna have this 3 by 3. And then what it does, it says, okay, I'm gonna do something with this 3 by 3 matrix to get a single number. And that's what it's called pooling. Max pooling will be, I get the maximum value of that. It can be average pooling, and it means it makes an average. Depends. And then once you finish that, now it's gonna start to connect to the dense layers. And it does need a one-dimensional one. So that's why we have the flatten there. So basically, it gets this very deep, in this case 32 channels. And then I guess, in some dimensions, I don't know exactly how many right now. Maybe 7. 7 by 7. And then it will basically flatten all that in a single array. And now it's ready for the dense layer. Okay? And that's when we add this dense layer, and then we see this already. So as a homework, or later you can ask me again, for the convolutional one, why? Why are they 320? Question. Huh? So try to figure it out a bit. Not you can bug me and then I will answer you. I don't know how much this takes. Hope not much. So, okay. So what we did here, you see, very easy. We added layers, right? We added what we saw already: the batch normalization, the dropout, but more importantly, we had the convolutional one. So the convolutional one in this case is 2D because it's an image in 2D. There's also 3D. Okay? Because you can also have NumPy arrays of more dimensions, of course. Right? So that will be sort of a video. Okay, so if I actually run this with the difficult data set, I'm going to get around, I think I get around, this goes very good, like almost 90% accuracy. But if I run it with the difficult one, maybe I should leave it running just to show you. I get around 30%. Okay, with this overkill model. Let me, 1 second. Let's just do that. Hopefully it just runs. According to me, it should. But like a colleague said, what is it? The supposition is the mother of all fuck-ups? There you go. My vocabulary is not that good. Yeah, so I think what is missing here is this tree. Oh, 28, of course. Yeah, the size of the data changed. The digits are, this is what I mean, that the dimensions are always the problem once you understand it. So the size of the image is different for the other data sets, so I had to change it. That's basically. So before I had 28, 28, one channel, now it's 32, 32, 3 channels. So I will leave it running a bit. So now let's move to the most interesting one. And also because we're mostly out of time. But I think the next one, you're going to have fun. Once you get to your house, you prepare some pasta or something. Okay, so let's see. So we're going to use the same data set, okay? But I'm going to talk to you about pre-trained networks. What does it mean, a pre-trained network? So a pre-trained network is a quite complicated network that a university or Google or somebody else did already. And they put it available. So the weights, they are available. That's the main sort of part. The weights after training these very complicated models are available to you. All these are available to you. Okay? So in this case, we're going to use, I believe, ModelNet. Why do I choose that? Basically because it will not take you that much to download it. And it's also pretty good. So if you see Inception V3, I showed you already, it's extremely, it's crazy, right? This is convolution, average pool, max pool, concatenation, dropout, fully connected, and softmax, and then it's all that stuff. So imagine if you have to train that on your laptop. Yeah, it's not bueno. Yeah, definitely. So it's great, right? If we already have the weights. And I'll show you why. So this is MobileNet. This is the one we're going to use. And it has also all this complicated stuff. Right? You can go through it if you want. So if you see, Keras already has a whole module for it, MobileNet. You can also replace this for Inception if you want. It's just Inception is a bit heavier, so it will take you a bit more. And what I basically did, I said, I look at the type of classes that these learn to classify. So this model available to you was the model that it was trained with the data set of ImageNet, which is 1,000 classes. So it should be able more or less to recognize this 1,000 classes. So I went into the type of classes, and I choose one. You just download a picture from internet. So yeah, so I downloaded this one. Okay, why? I don't know. I'm a Scorpion. I guess I was biased on something. But anyway, so for me, this image, I will say it's not extremely difficult, but the tail, especially how it bends with the background, I don't know. Anyway, so if you see, we already have the model, right? We loaded the model here. We just basically this line, MobileNet, weights, ImageNet. And then we just basically adapt this image to the inputs. It's just basically this land. This is what it's doing. And it's going to predict. And there you go. Scorpion, 99% sure. You know what this means, right? This means that you can use it. You can come up with a brilliant idea, and it's there already. You don't need to train it. Of course, it has to be one of these classes. Okay, so now comes the interesting part, right? Because now you're bound to the classes that they train it for. But now let's say you have this brilliant idea. I want to detect, I don't know. For example, I have a problem with choosing glasses. They're all ugly. So you want to say, to filter them if they are good or not. And you want to have somebody that labels. And I want to adapt this to detect that. So how do you do that? I think we're running out of time, but... So in this case, I didn't do it with the glasses, but now I want to do it for this data set, the same data set that was really difficult before. So what I'm going to do here is, what this is doing is actually creating a, put them in a disk. It's putting the images on my disk in a directory way. So, because normally this is the way you're gonna have your data, right? In actual files, not by Keras giving you a prepared data set. So that's why I want to make it more realistic. So this is more or less. So this basically prepares it for you. Okay. It's going to take a bit, I think. But let me make sure. Maybe it's because this is running. So now, if I go... okay, so at least it already created it. Yeah. So you can see Yeah. So right now it's creating the training data. So basically you just need to separate your files like this. You point to a file, and then each of the classes, you put the name to the directory, and then inside, you just put your images. It doesn't matter what name you give to the images. So now what this is going to do, okay, let's give it a look. I'm going to kill this one. Okay, so I have no clue why is this taking so long. Okay, I'll stop. Okay, hopefully it did put already some of them. Yeah, okay, so these are the images that are, so there are some inside. Okay, so now what I'm going to do instead, I'm going to load, but I'm going to add this flag which says include top false. What does do is that it will give me the whole thing with the weights, but it's not going to give me this little part here. Why? Because that's the part that classifies. Remember we talked about these hierarchical features? So I'm going to get the hierarchical features from everything that was trained, but it's not going to give me the other, let's see, we have it here. So if you see here, so I have 5 minutes. So you see there's no softmax anymore. Right? So now what do? Now what you do, and I have to probably hurry up, is add them myself. First, what I said, right? You make those layers not trainable. You freeze them because, well, it would be completely very, very expensive for you to do that. So what I do here is basically add them. So I basically send the base model, which is the one we just loaded, and then I add a pooling, I add a dense layer to make these connections, and then the final output layer, which is a softmax. And basically, I only have 3 trainable layers instead of having 22, and 22 which are quite complicated. So now if I do this, I compile it. Now it's categorical cross entropy, of course. I'm not going to be on time on this, I think. So this will be a way to get it from the file. So this will be data C410 train. So I want the image to be rescaled, so that means it's going to be multiplied by this value, and I believe that's it, all I need. Now I'm going to send this. I'm going to read from the file a batch size of 50. And I know that my model that I loaded receives 128 by 128. So I don't have to pad it the images. This is going to do it by itself. I believe is this. Oh, maybe this is the one. This doesn't do anything. I see. Let's see. So here what I'm going to say to it is that cval, what is cval? 0? Okay, let's just do this. Right? So it went and found the 10 classes with 48,000 images. Right? But they're not loaded in memory. That's very important. It's not loaded in memory. So now when I train it, sorry, Vincent. Let's see here. Just one more. So basically, I define, the number of epochs that I want and the steps that I want in the. Missing something. Oh yeah, and I need to put this one more, and that's it. Yeah. So now what I'm actually doing, it's getting the data from disk and doing these changes, multiplying by 1 to 35, doing the padding for us already. You can also augment the data by saying, I want to also rotate randomly, or zoom in or zoom out randomly. So the great advantage is this, that you read from disk, right? You don't have it in memory, and you also have the data augmentation and preparation already for you. This is and 4 lines of code, right? So Keras is extremely easy. And I would advise you to increase maybe the number of epochs, and you see because you're using this architecture, it can get up to 80%. With the other, the overkill model, it gets to 32% or something. This is because we're leveraging, in these scales, mobile net weights. And with that, I guess 1 minute in time. Thanks.